Greetings and welcome to lecture number 10 on the course Introduction to Fourier Analysis. On the last lecture, we concluded our treatment of Fourier series, Fourier coefficients and 2π periodic functions. Now we begin investigating Fourier integrals and Fourier transforms. The Fourier transform is the substitute of Fourier coefficients for functions which are not necessarily 2π periodic. The Fourier integral, on the other hand, is the substitute of Fourier series for such functions. Virtually all of the results for Fourier series we discussed in the previous lectures have natural analogues in the non-2π periodic setting. However, even the basic definitions in the non-2π periodic setting are more involved, and we will quite likely not have time to cover these analogues carefully. Pursuing these topics further provides a fine variety of topics for bachelor's and master's theses. Let us then get started. First of all, why can't we just define the Fourier coefficients exactly in the same manner as before? Namely, f hat xi equals the integral over the box T of fx times e to the power minus I x dot xi dx. If the function f is not 2π periodic, it is not completely determined by its values on the box T or any other box of finite measure. So, if we define the Fourier coefficients in this way, we would lose information. We would lose track of the values of f outside T, and there would be no hope to recover the function f again from its Fourier coefficients. In other words, the Fourier transformation would not be invertible. This is why an integration over the whole space Rd will be necessary in the definition of the Fourier transform. Before moving to the details, let's redefine some of our basic notation, which was earlier adapted to the setting of 2π periodic functions. First, the notation LP will, from now on, stand for the space of Lebesgue measurable complex-valued functions defined on Rd, whose LP norm is finite. The LP norm is defined in the familiar way. If the exponent p is less than infinity, the LP norm of f is the integral over Rd of the pth power of the absolute value of f, and finally the whole integral raised to the power 1 over p. And if p is infinity, then this expression is replaced by the essential supremum of the absolute value of f over Rd. To emphasize the obvious, any reference to the box T is gone from these definitions, and also there is no longer a normalization by 2π to the power minus d. The notation Ck will stand for the space of all k times continuously differentiable complex-valued functions defined on Rd. For k equal to 0, the notation C0 is abbreviated simply to C. Of course, these functions are no longer required to be 2π periodic. Then, as a new piece of notation, we define the space calligraphic D to consist of those infinitely differentiable functions on Rd whose support is compact. Quite often in the literature, these functions are referred to as test functions, but since the words test function can mean many different things depending on the context, you should always be a bit careful when using this terminology. Note that the function f belongs to the space D if and only if f is infinitely differentiable and there exists a positive radius r such that fx equals 0 for all vectors x in Rd with norm exceeding r. Indeed, this condition clearly implies that f has compact support, and conversely, if f has compact support, then this support can always be contained in some ball of finite radius r. We also redefine the notation for convolution. If f and g are two L1 functions on Rd, we define their convolution to be the function whose value at x in Rd equals the integral over Rd of fy times g x minus y dy. Just as in the case of 2π periodic convolution, it follows from Fubini's theorem that this integral is absolutely convergent for Lebesgue almost every x in Rd, and defines a function in L1 as x ranges in Rd. Now that the basic definitions are in place, we can give the definition of the Fourier transform for L1 functions. As we discussed earlier, you should view this definition as the analog of Fourier coefficients for non-2π periodic functions. Let f be an L1 function and let xi be a vector in Rd. Then the Fourier transform of f at xi is the integral over Rd of fx times e to the power minus 2 pi I xi dot x dx. As you can notice, we now post this definition for all vectors xi in Rd and not just those with integer components as in the case of Fourier coefficients. Therefore, the Fourier transform defines another function on Rd. Furthermore, note that the integral is absolutely convergent thanks to the assumption that f is an L1 function. And observing, as we have done many times before, that the modulus of the complex exponential is identically equal to 1. As a more precise version of this observation, let us record that the absolute value of the Fourier transform f hat is bounded from above by the L1 norm of f. The proof of this observation is straightforward. Fixing xi in Rd, the absolute value of f hat xi equals, by definition, the absolute value of the integral over Rd of f times a complex exponential. Then we simply move the absolute values inside the integral, which makes the complex exponential vanish and leaves us with the L1 norm of f on the right-hand side. You might have already noticed that the normalization, or more precisely the definition of the complex exponential in the definition of the Fourier transform, is a little different from the one we have seen in connection with Fourier coefficients. Namely, we have placed an additional factor of 2 pi in the exponent. This is only a matter of convention. It seems to me that many formulae for the Fourier transform are simplest to state and remember with this normalization, but other lecturers will surely disagree. So, please bear in mind that other conventions for the Fourier transform are also common in the literature. The corresponding formulas will then involve additional or fewer factors of 2 pi. The most commonly used alternative definitions for the Fourier transform are the following. First, f hat xi equals the integral over Rd of fx times e to the power minus ix dot xi. And second, f hat xi equals the square root of 2 pi to the power minus d times the integral over Rd of the same expression as in the previous alternative definition. In Wikipedia, you can find a long list called Table of Common Fourier Transforms. All of the transforms in that table have been repeated 3 times for each of the 3 possible definitions above. But of course, if you know one of the 3 Fourier transforms, the other 2 are easy to deduce by an elementary change of variable in the integral. Now we have the definition of the Fourier transform for all L1 functions on Rd, not necessarily 2 pi periodic. This wasn't too difficult, so what's the issue here? The difficulties only start to emerge when we attempt to define the Fourier transform for LP functions when p is not equal to 1. You might recall from the previous lectures that most of the deeper results for Fourier coefficients and series concerned somehow L2 functions, or perhaps L2 Sobolev functions. So we would very much like to define the Fourier transform at least for L2 functions. In the 2 pi periodic world this was easy for the reason that the higher exponent 2 pi periodic LP spaces LP of t are all contained in L1 of t. So any definition for functions in L1 of t automatically works for all functions in LP of t. Such inclusions are no longer true for standard LP spaces over Rd, which we are now considering. There are no general inclusions of the form LP would be contained in LQ of Rd, and in particular the higher exponent LP spaces are not contained in L1. The only reason why such a statement was true earlier was that the box T had finite Lebesgue measure, but of course the whole space Rd has infinite Lebesgue measure. This fact presents a serious challenge for defining the Fourier transform of a function f which lies in L2 but not in L1. In this case, the integral we previously used to define the Fourier transform is simply not absolutely convergent. So, if we still wanted to use this integral expression to define the Fourier transform, we would need to interpret it in some other way, some limiting sense. In fact, this would eventually work for L2 functions, but there is a conceptually neater way to proceed, which we will next discuss. As a brief summary of what is coming up next, let us say that despite this difficulty of non-absolutely convergent integrals, the Fourier transform can eventually be defined for all LP functions for all exponents p, and even far beyond. Furthermore, this definition can be done in a simple and highly useful way. The full details of this definition will come much later, but we can explain the rough idea straight away. An excellent analogy to keep in mind is the definition of the weak derivatives we discussed on previous lectures. Recall that if f was a function in L1 of t and alpha was a multi-index, then the weak alpha derivative of f was some function g in L1 of t satisfying the following integration by parts formula. The average integral over t of f times the classical alpha derivative of phi equals plus or minus 1 times the average integral over t of g times phi. And this formula was supposed to hold for all possible test functions phi, which were infinitely differentiable and 2π periodic. This definition of weak derivatives is a very powerful idea. It allows us to define a useful concept of a derivative for any L1 function f without caring at all whether f is classically differentiable or not. We would like to adapt this idea to define the Fourier transform in some weak sense for all LP functions and possibly beyond. How to do this? The motivating observation behind the definition of weak derivatives was the integration by parts formula, which was true and easy to verify for all smooth functions, and which was eventually taken as the definition of weak derivatives. What is the analog of this formula for the purpose of defining weak Fourier transform? The answer is the following formula, which is often known as the duality formula. Let f and g be L1 functions. Then the integral of hat f times g equals the integral of f times g hat. Note that these integrals make sense and are even absolutely convergent. We already have a definition of the Fourier transform for L1 functions, and we have also observed earlier on this lecture that the absolute values of the Fourier transform are bounded by the L1 norm. The L infinity norm of f hat is bounded by the L1 norm of f, and the same inequality holds for g. Hence, for example, the integral of the absolute value of f hat xi times g xi dxi is bounded by the L infinity norm of f hat times the L1 norm of g, which is finally bounded by the product of the L1 norms of f and g. The proof of the duality formula for L1 functions is just an application of the definitions and Fubini's theorem. Namely, start from the left-hand side. The integral of f hat xi times g xi dxi. Then unwrap the definition of f hat xi to find the double integral over both x and xi of fx times g xi times e to the power minus 2πi xi dot x dx dxi. When this double integral is rearranged using Fubini's theorem, it equals the right-hand side of the duality formula, namely the integral over Rd of fx times hat gx dx. The duality formula for L1 functions proved above plays the same role to the weak definition of Fourier transform as the integration by parts formula played for the definition of weak derivatives. For a function f, we would like to define the weak Fourier transform to be a function g, which satisfies the duality formula for all possible test functions phi. Namely, the integral of f times the Fourier transform of the test function phi equals the integral of g times the test function phi. This is not yet a rigorous definition for two interrelated reasons. The first one is that we haven't specified the collection of test functions phi in the formula defining the weak Fourier transform g. If our test function space is the empty space or only consists of the zero function, then the formula holds for every function g. In other words, every function g is the weak Fourier transform of f if the test function space is trivial. This is evidently not a very useful definition. So, we want the test function space to be so rich that if the formula defining the weak Fourier transform g holds for all test functions phi in this test function space, then the function g is uniquely determined. But if the test function space is fairly rich, then we encounter a second serious issue in defining the weak Fourier transform. Does there exist even one function g on Rd which satisfies the defining equation for all test functions? For example, we could require that the test function space contains the space calligraphic D of infinitely differentiable and compactly supported functions. Then, if f is an LP function, does there exist a function g, maybe in some other LP space, such that the integral of f times hat phi equals the integral of g times phi for all functions phi in calligraphic D? This is a highly non-trivial question. If f is an L1 function, then the pointwise defined Fourier transform f hat is an L infinity function which satisfies the equation even for all L1 test functions phi. This was the content of the duality formula which we proved a little earlier. Later on these lectures, we will show that the situation is similar for all LP spaces when the exponent p is between 1 and 2. If f is an LP function and p is between 1 and 2, then we may associate to f a unique function g in LQ, where q is the dual exponent of p, in such a way that the weak Fourier transform equation is satisfied for all functions phi in D. In other words, the weak Fourier transform of an LP function is an LQ function, if p is between 1 and 2. Maybe surprisingly, the situation changes radically when the exponent p exceeds 2. If f is an LP function with such an exponent, there may not necessarily exist a function g satisfying the weak Fourier transform equation. One does not even have to look for very exotic examples. In fact, if f is identically 1, then the weak Fourier transform equation is not satisfied by any function g. Instead, it is satisfied by the measure delta 0, which is known as the Dirac mass at the origin. The Dirac measure of a set A equals 1 if 0 lies in A, and otherwise the Dirac measure of A is 0. We will return to this example later and do it much more carefully. The only point we want to make here is that the existence of a weak Fourier transform is far from clear, even if f is something very simple. And sometimes the weak Fourier transform can exist as an object which is not a function. Even more generally, if f is a wild and exotic function such as f of x equals x, then the weak Fourier transform of f turns out to be something called a tempered distribution. These will be defined and studied at the very end of the course. We have now seen a brief glimpse of things to come in the next lectures. Of course, everything will be repeated much more slowly and carefully. On the next lecture, we will begin the journey by defining the correct space of test functions. These are known as Schwarz functions. This concludes lecture number 10 on the course Introduction to Fourier Analysis.